All right, so we have a great, very timely, I think, hot off the press education session today from Henrik Edstrom, Distinguished Architect in Graphics at Autodesk. He's going to talk about USD on the web and implementing WebGPU and the Hydra Storm Renderer. I think it's a great topic, right, to see what, what's reasonable and what can be done and what kind of the performance and the trade-offs are for USD on the web. And Henrik has done a ton of work in the materials world. When I first met him and I went back and I searched my Gmail, I think it was in 2018, and Henrik gave a talk to the Kronos 3D Formats group on standard surface. And then, I mean, really was a driving force getting Autodesk involved in Kronos and then working on PBR next. So, it's brought a ton of knowledge and enthusiasm there, and I think across the industry. So Henrik, look, I'm really excited to be one of the one of the people in the audience for your talk. So I'll stop the screen share and send it over to you.
Thanks, Patrick. Yeah, very much appreciate the opportunity to talk here today. So first thing I want to mention is that I have a co-presenter, Aura Munoz, who is our main engineer on the WebGPU project. We have several other people involved as well. So what we're presenting here today is not just Aura and myself, it's the work of many team members. But Aura is really going to dig into the meet and greet of the details of WebGPU and how we handle that. But I don't think we've had an opportunity to present to this group some of the work we've been doing in bringing both USD and actually MaterialX, traditionally, C++ libraries used in a desktop environment, and bringing them to the web. So I'll start with a little bit of context and then why we're doing this and the work we've done so far. And then Aura will go into more details in the most recent work we've been doing around WebGPU and Storm on the web. So just to start off, I just want to emphasize the importance of open standards and open source to Autodesk, and especially what we're doing in the area of graphics. So for this talk, we're mostly going to talk about USD, Hydra, MaterialX, and of course WebGPU, but we are involved in many other graphics-related standards as well. These are just a few of them. And Autodesk is, of course, a member of Kronos, W3C, ASWF, and the Metaverse Standards Forum, naturally. So just emphasizing the key role that open standards and open source play in what we're doing in graphics. So just going kind of historically, what we've been doing, bringing some of these C++ libraries to the web. We started with MaterialX, so I'll go over that pretty quickly. Again, setting the context, why is MaterialX important to Autodesk and why are we investing in that? Obviously, it's a very inexpressive, flexible graph-based system for materials, originally developed by Lucasfilm and ILM, later open sourced. Autodesk and many other companies have very actively contributed to MaterialX since. And we feel it's really the right abstraction levels for materials. It describes the intent of the materials and not the implementation, which makes them authoring tool agnostic and render agnostic and allows us to target both high and offline rendering and various different real-time systems. And it also makes it future-proof. We're not tied to any particular shading language or what the current APIs are able to express. MaterialX can also express various different shading models, or PBR shading models, including standard surface, of course, but also GLTF PBR and USD preview surface and so on. And we actually had a very similar initiative at Autodesk many years ago, trying to come up with a similar graph-based system. But when we learned about MaterialX, we decided to drop our proprietary system and instead focusing on contributing into MaterialX. So these are just a few of the contributions that we made over the years. And I'll talk a bit more about the web support contributions in a minute. I also want to mention standard surface again, and why we focus so much on that. So of course you can express any shading model you want in MaterialX, but there are benefits to try to align on one main model that can be used for most materials. And standard surface is really a production proven, very simple and intuitive shader that is well suited, from a kind of user perspective in designing most of the materials that you will need in practice. And it's also easy to map to and from other common material models, since we have this well-defined Uber shader, so GLTF PBR next and USD preview surface. We have well-defined mappings back and forth from those to standard surface. And it can really express the vast majority of materials that you will encounter in practice. And that's across both film VFX and architecture and design visualization, which are obviously big areas for Autodesk. And just brief history, like these are some of the earlier publications that have kind of led to the standard surface specification that we released in 2019. And as we announced at GDC earlier this year, we are working on an initiative to align standard surface with Adobe standard material. So that's still work in progress, but hopefully there's news to share on that shortly. But that's kind of really just evolving standard surface to the next iteration of it. It's not going to be any major changes, but getting some of the things that Adobe had worked on, just getting one model so we don't have two. I think that's going to benefit the whole industry. So very excited about that development. Okay, so on to MaterialX for the web and some of the contributions that we made there. Again, MaterialX is a C++ library, but we added a WebAssembly build and JavaScript bindings for the library itself. We also extended the shader generation framework, so you can generate WebGL2 compatible shaders. And those are agnostic of any particular framework or renderer, so could easily be used in 3GS or Babylon or Play Canvas or your engine of choice. And we also added a MaterialX viewer for the web. So all of this work has actually been incorporated into MaterialX as of version 138.4, so over a year now, and it's readily available in all browsers. And this work has since been picked up by others. One good example is the AMD MaterialX, the free MaterialX library that is available on GPU Open, and it uses the MaterialX library and shader generation behind the scenes. So this is just to highlight some of the earlier work we did on kind of bringing C++ libraries to the web. If you are interested in learning more, if you maybe want to contribute to this project, the MaterialX Slack channel on ASWF Slack is a great way to get in contact with the group and start to contribute. And there's a lot more work to be done around MaterialX on the web and making that a better experience, optimizations, trimming down the bundle size. And speaking of WebGPU, we don't have native support for Wixel, the WebGPU shading language in MaterialX yet, so that's something we're looking forward to add. So that's on MaterialX. So that's something we did a couple of years ago. After that, we started looking into bringing USD and Hydra to the web. So I just started with some quick concepts. Most people in this group probably are well familiar with USD, or OpenUSD as it's branded these days. But some of the aspects that stands out to us is that it's much more than just a file format. It's really more an extensible framework for collaboration and editing of very complex scenes, a very complex project. So there is a clear difference there with the kind of the intent of USD versus what we're doing with GLTF, for instance, which is more focused on delivery and finalized assets and making them very portable, very much the JPEG of 3D. Whereas USD is more focused on kind of the editing and authoring and collaboration workflows and supporting robust interchange of scenes between mostly creation and authoring tools, and those can come from many different vendors. So I won't go into more depth on the scene description aspects of USD, but it does have some other very interesting components to it, like the Hydra rendering abstraction layer and a Storm rasterizer. Our vision is really quickly, Hydra is this abstraction layer that decouples the applications from the renderers. So it's pretty much a plug and play framework where you can interchange different renderers, and you can either swap out renderers or make significant changes to the renderer without the applications being aware of it or affected very much. So that decoupling between applications and renders is very attractive to us. And then Storm is, of course, the open source rasterizer that comes with the USD library, and that's something that we're very actively looking at from Autodesk. So our vision is really to see if Hydra can be a viable solution across desktop, mobile, and web. So just a brief primer on Hydra. You basically have two APIs: the scene delegate API, or scene index as it's now called in Hydra 2.0, and you have the render delegate API. So the scene delegates are responsible for feeding the scene graph basically into Hydra. So that could be either a USD scene graph or just a custom scene delegate for whatever scene representation you might have. So we see this as a great opportunity to feed scene data, whether it comes from a desktop application, mobile app, or web application. They can all be communicating with Hydra without really having to think about how it's going to be rendered, or what API is under the hood, or if it's a rasterizer or path tracer and whatnot. And then on the render delegate side, you can use different render delegates. I'm just going to touch on the ones that we are most actively working on from Autodesk. So the first one is Storm. Again, it's a rasterizer, and it comes with the USD library as open source. Another renderer is Aurora, something that we open sourced last year, and that's really a real-time path tracer focused on like realistic real-time viewports, where you need realistic shadows and materials and global illumination. So some use cases where a ray tracer or path tracer is more probably gives you more than a rasterizer like Storm would do in this case. So if you're interested in that, that's also available on GitHub, something we fully open sourced. Also, of course, we have Arnold, which is our production renderer, which is focused on like the very high end rendering use cases. And while it's interactive, it's primarily focused on offline rendering. USD also provides the Hydra graphics interface, which is the abstraction layers over the various different APIs. So it had OpenGL support initially, then Apple added the Metal support. There's Vulkan support that is getting pretty mature now. And these are used by Storm and actually also by Aurora. So this abstraction layer makes it easier to target the different APIs to address different platforms. And like I mentioned here on the top, mobile is interesting to us as well. So having Vulkan for Android and Metal for iOS and iPads is something that we're very interested in. Last week, we actually open sourced a DX12 backend to HCI as well to be able to run Storm through DX. And there are some benefits to that. In particular, there are some of our products that are relying on the Warp software rasterizer. And there's, at this point, at least, not any Vulkan equivalent to that provides the same capabilities and the same robustness as Warp. But there might be other benefits as well. And I know the USD game community has been showing some interest in maybe having native DX support. And then, of course, the thing that we open sourced this week was the WebGPU backend for HCI that Aura is going to cover in more detail. But this is kind of the big picture and where we're going with this, and the benefits is being able to use the same stack across desktop, mobile, and web is very attractive to us. And also, the decoupling here with Hydra is very attractive, and the flexibility of using different render delegates. And also, what Storm provides today is also, is quite capable. So that's why we're investing further in that and seeing how we can improve Storm and add the capabilities that we need for our products and workflows. So the earlier work we've done on USD and Hydra and bringing that to the web started a couple of years ago. First, we added a scripted target, a build target to support WebAssembly. We also had to do some fixes in third-party libraries like the dependency on TBB. Pause this one for a second. We added JavaScript bindings for USD and Hydra, so you can use both of the libraries from your JavaScript application. And we also added an initial render delegate. This was more as an example, but it's based on 3GS, so that's what you see up here in a little video. Coming across poorly on my end there, so I'll probably pause the video. So this is work that we did in 2001, 2002. These earlier PRs are still available, but they've been superseded now by the more recent work and that we released this week. So in addition to supporting what I mentioned here on this slide, it also includes the Storm Renderer and the WebGPU support that Aura is going to go into detail on. If you're interested in knowing more about this or starting to contribute, again, there's a lot of work to do here to make USD and Hydra like a better experience on the web. Lots of optimizations and feature gaps that needs to be filled and so on. But again, the USD Web Working Group Slack channel on ASWF Slack is a great place to start. So with that, I'll hand off to Aura to talk more about the Storm and WebGPU.
Sure, just share my screen, just a second. Oh. Okay, and yeah, sorry. Okay, so yeah, I want to talk a little bit about the recent work that we have been doing to bring some of the rendering capabilities from USD to the web. So before going into details, I wanted to walk you shortly through the history of web graphics to give you some context on why WebGPU is such a exciting new web API. So it was back in 2011 when we had the first graphics API in the web with WebGL 1, and which was based in OpenGL 2.0, which is just a subset of OpenGL. And it took 6 years to upgrade to WebGL 2, which had a lot of benefits. But during that time, you could see how there were a lot of new graphic APIs that started coming up, such as Metal, Vulkan, and more modern versions of DirectX. And basically, these APIs were trying to be more performant and be closer to the hardware and give you more access to the new capabilities of, for example, new hardware development. So in 2017, it started the definition and the specification of WebGPU. And it just until I think a month ago or two that it was just released in Chrome. So it's in my opinion, a very exciting time, at least for the web. So in general terms, WebGPU, it's not a replacement of WebGL, it's the successor, so it doesn't replace completely. And as I said, it is closer to this newer APIs such as Vulkan. It's a little bit simpler, but if you look at the API, you can see a lot of parallelism there. And it has been more than 6 years in the making. And usually in the browser, things take a little bit longer because they have to reach a standardization process through all of the major browser developers. So for example, in the standardization process, Google, Apple, Mozilla has been working in reaching this 1.0 specification that it's just released or it's in the making. So this is kind of an example of what you can do now on the web with graphics. So on the left, it's basically a C simulation using compute shaders, and it's using Babel.js, which is a web graphics framework. And on the right, it's something that it's not available yet in WebGPU, maybe next year, but this is just an example of how extensible it is. And this is somebody that basically created an extension using the WebGPU API. So this is another example of how much more performant it is. So this is basically the same model, and it's running again in the same framework, but now one it's using the WebGPU renderer. And as you can see, as the frames per second are comfortably at 60 in WebGPU and WebGL. It just drops frames to 15. And as I said before, one of the most important contributions to this new graphics API, it's the compute shaders, which were not accessible with WebGL. So on the left, it's a benchmark on how long it takes to do matrix computation. And you can see how WebGPU, it's orders of magnitudes faster. And this is not just exciting for graphics folks, but it's also very interesting for the machine learning community, because most of these computations that you have are basically just multiplying matrices. And so it makes it closer, it brings it closer to basically what a native application can do, while before we were quite far apart. And on the right, it's just a benchmark on trying to recreate how game engines would work, which is basically see how many triangles with different attributes, which means that you define different uniforms or binding groups, how much of them you can render while still keeping 60 frames per second. And you can see that even in the worst case scenario, it's 2 times faster. So it brings a lot of benefits. So this is a very new technology, and as I said, it just released in Chrome in version 113. I think, again, this was just a month ago. And Firefox has it. I think it has an estimation to have it by the end of the year in production. And Safari is in development, so this one doesn't have a timeline yet. And this developers, together with the standardization group, have been working as well with a lot of the most important partners on the web regarding graphics and GPU computations. So for example, Babylon.js and Free.js, they both have been re-implementing their shaders and their materials and their renderers to adopt WebGPU. Similar, they have been working with the TensorFlow community just to iron out the API such that it's usable for those main use cases. So now I want to shift into why we chose WebGPU when talking about USD. So one of the things that it's very useful for us, and I will come back to that later, it's that you can develop natively and it's cross-platform. So you can target Windows, Mac, and Linux machines, as well as the browsers while developing with WebGPU. And it also, as I said, and I just want to emphasize it because it's a big thing, it unlocks the compute capabilities we were not accessible with the WebGL API. And then it's closer to graphics, to this modern graphics API, which align better with the basically USD existing code that it's already there. So Henry talked a little bit about Hydra, so I don't want to spend much time here, but I just want to scope the conversation to say that we will be discussing only HdStorm, which is the real-time rasterizer. And this is what we brought to the web with WebGPU. So this is currently how the HdStorm render pipeline would look like. So you have the sim delegate and the Hydra framework, and then the render delegate, which is HdStorm. And then you have this abstraction layer, which we mentioned that it already has some mature implementations for OpenGL and Metal. And now Vulkan is also reaching a more mature state. And basically our contribution is just extending this with the WebGPU API. So what this involves, it's basically interpreting all of the HCI and platform independent representations or commands into WebGPU commands. So that involves basically creating some classes to handle buffers, textures, samplers, the shader functions, as well as the graphics command and the compute commands. So one of the things that we also wanted to bring from HdStorm was all of the materials that it had and a lot of the other computations. So most of the things are encapsulated in shader code, of course. And so we had to see how we could feed a WebGPU with the existing shader code. So also to give context, WebGPU introduces a new shading language called Wixel, and it's significantly different than DLSL. So what we did was developing a solution that basically would translate the final DLSL code into SPIR-V, which is an intermediate bytecode representation of shaders. And that we do it using shader-C. And finally, we use Google Tint to translate from SPIR-V to Wixel. So as this was a complicated pipeline and system, we divided the development in three steps. So first, we implemented just the ACI WebGPU APIs, and then we developed a small application where we interacted directly with it to render simple models. And this allows us to have a much simpler application and render pipeline that we could control, and then we could see the gaps of the APIs that we were missing, at least for the first workflow that we wanted to achieve, which is just the minimal one. So second, we tried to tackle HdStorm whole render pipeline. So basically, again, that involves loading a USD model, and then from loading the model to showing it on the screen. And for that, we use Dawn, which is Google WebGPU implementation. So that's basically what's running behind Chrome. But you can use it as a library, and then you can develop natively with C++. And that it's very helpful because then you can use native debugging tools, as well as the native graphics debugging tools. So in my case, I was able to use the metal debugger. And also one complexity that introduces that it's multi-threaded, which is a little bit harder to debug in the browser. In general terms, WebAssembly, it's not that easy to debug, but with workers, it's a little bit more complicated. So this made it much easier. Finally, after we thought that we had most things done, we compiled the whole project using mscripting into WebAssembly. And then we developed a very small application that was using the GL engine to load a USD file and then feed that information to Hydra, and then that use HdStorm to render it. So what you see here, it's USD View, and this is a tool that comes in the USD repository, and it's usually used to inspect the USD model. So on the top left, you see the hierarchy of the model and some attributes, some information. And on the top right, you see the viewport, which is using HdStorm. And in this case, it's using WebGPU to render all of the meshes and all of the information. So now I want to stop briefly and show you just a few models, but to see that it's running on the web. So this is exactly the same model that you saw in the desktop application in USD View. You can see how you get the exact same image, and that's of course because it's using the same shaders and the same render pipeline. So this is just a few other models that are using some different either attributes or materials. So let me go back to the presentation to give a breakdown on kind of what you saw. And I know that the models that you saw may look simple, but if you look under the hood, there's a lot of things going on. So in general terms, by enabling all of the USD ecosystem from an end-to-end workflow, you get a lot of functionality. So you have the USD file loader, which allows you as part of the USD functionality includes these compositing capabilities as well as collaboration. You also have the Hydra rendering framework, which has a highly optimized rendering system. It also brings the flexible plugin system of USD, which basically allows you to define different schemas and define different functionality as a form of a library. You have the scene delegate with USD imaging. And we also bought the rendering capabilities of the rasterizers with HdStorm. And this library, it includes a lot of things as well. It includes efficient mesh batching. It also includes the highlights for faces, points, and edges. It includes a lot of ELSL materials. It includes compute shaders, for example, to calculate the smooth normals or the frustum accelerated with GPU. You also have a USD preview surface support, which is a node model material and similar to MaterialX. You also have color correction tasks to go over the generated image. As I said, you have cross-platform support, so you will get the same things for Windows, Mac, Linux, and now the browser. There's a couple more things that it's running underneath the demo, but this is like in general terms what you get. So we're in general terms very excited on what we managed to achieve, and we're looking forward on what we could do next. But of course, there were some limitations. And one of the biggest limitations, in my opinion, is the hard 4 GB limit of mScripting web applications. And that's due to the fact that WebAssembly has 32-bit system, and it has been worked on the 64-bit system, but it's still in development, and still no deadline or whatnot. The other thing that was difficult is that it doesn't, the open subdiv library, the shaders are not compatible with Vulkan and therefore not Boost per V, so we couldn't use that capability, which is really important in the context of the USD ecosystem. And we had to introduce this runtime solution with from DLSL to Wixel, and this introduces two dependencies, which is shader C and tint. And these are quite heavy because they have this Vervi tools and a couple of other libraries. And there were some conciliation problems on how the WebGPU API was specified and how the whole HdStorm and HDI system was specified. WebGPU, in general, it's more restrictive. It's not more, you have to be more explicit rather than leave it to interpretation, like in OpenGL. So for example, you have to be explicit on where the attribute location, and it doesn't have the interstate connection basically based on the name. And there were also some limitations just regarding the WebGPU API, but I just want to also, before jumping into this, just give the caveat that this is a very, very, very young API. Again, it was just released a month ago, so things might change, and it's designed in a way that it will be able to grow, and it might address many of these issues. But in our case, there were several missing functionality, either in the API or the shading language. So for example, the GL primitive ID doesn't allow us to load several models due to some interpolation of the UVs that use this kind of variables. And the other thing that we were facing was that we reached some of the limits. And again, I just want to explain a little why these limits are so low. So WebGPU has to basically serve all of the backends, which is Vulkan, WebGPU, and DirectX. And basically, it can only expose usually the most constrained version of all of the APIs. And it also cannot check at runtime if, for example, your machine has a higher capabilities, because it could give away some of the information of your machine, which proves to be a security and privacy concern for the web. where you can do fingerprinting and try to exploit some particular hardware. And there are many things that we want to work on. One of the biggest problems, and this is due to how the USD plugin system works, it's the bundle size. It's really big. We need to do some optimizations. It's not usable for production like that. And that's because mscript and dynamic libraries, they don't work the same as you would have in a desktop computer where you have the file system. So that led to not being able to optimize on some part of the code with the compilation flags, for example. And we want to look into the MaterialX integration. And yeah, that's all from my side.
All right, yeah, happy to take any questions.
I would love to know if, let's say you were able to do a lot of those optimizations you presented on the last slide, because to me, that last slide, that 70 megs is sort of, it means that it can't be used in any end user scenario. It would be very good for like an editor, like creating like My Online or something. If you could do all the optimizations you're imagining, what do you think the end size would be?
So for first release, not release, but for the first USD script, PR, sorry, we managed to get the bundle size to 1 point something megabytes.
Yeah, I think it was 1.2 megabytes, but
That's a
yeah,
subset.
that's USD and Hydra, and without a lot of the plugins. So we need to figure out another way to deal with plugins. Maybe you can add something to that, or
yeah, the thing is that in the case of the file system, we just didn't spend much time. But what happens with the USD and how it is basically flexible, it's that you will load a file, and while loading the file, you will see what kind of extensions you need. Let's say that you will need the light extension, the USD preview surface. And what we did, because again, like it's more complicated, we so far has just instrumented the code to build static libraries. We basically bake most of the plugins there. So as I see that we could work toward a more production, adaptable thing, it's that when you load the file, right? Let's say that you need, again, the live plugin, you will do an HTTP request, and then you will get that file only. And then you could cache as well all of these plugins, because they will be independent HTTP files. Yeah, HTTP calls, right?
Amazing. The other question I had, 1.7 megabytes. I can't believe you got it that small. That's phenomenal. So there is like hope. That's amazing. How does this relate to Safari's model tag? So I understand that it somehow has a USD library in it, and it may expose an API at some point.
I don't have any insights over. There might be someone else on the call who can speak to that. I'm not sure who's on here, but yeah, we did look at that early on when the first proposal came out, and something like this could actually be used under the hood. But I'm not familiar with what Apple is doing there, but maybe someone else is.
I think with the Apple, I think they usually do the announcement just when it's released, so it's hard to know, hard to speculate.
Yeah, I guess I don't know. I guess it would be not good to put the whole USD bundle in Safari because it'd be an attack surface. So they're probably not going to expose it, even though they're including it. It's too bad.
Right.
Yes, exactly. Probably you could see it, like as you see a PDF on the browser, but I don't know if you will have an API, because to have an API through the browser, usually you have to go through a lot of standardization. So I don't think they will go on the wild and just have a browser API, I guess, but this is, again, speculation.
Gerald, do you have a question?
Yeah, so you just said 70 megabytes, including the full stack with WebGPU. Do you remember the code size when you were using Hydra Delegate based on 3GS?
Yeah, that was 1.2. And that was not, we didn't really spend any effort optimizing that. So I have no idea how much further we can push that, but that was, yeah, just over 1 megabyte.
Okay, thanks.
Was that the WASM or the whole thing?
That was the, I think that was the whole thing.
Okay, I remember.
Well, it might have not have included the render delete, but 3GS is pretty small, so I don't think that would add much on top of it. But
David?
Yes, hello. Thank you very much for the nice presentation and really great work. I have a question. I see, or I understand that Hydra and USD are being like presented or kind of together, and I wonder, is there the idea also to kind of decouple USD from Hydra? So is it a valid scenario to just use Hydra with custom delegates and then not use any of the USD parts? And so you mentioned these USD plugins, and I'm not so familiar with USD. Is that contributing to the size? And is that part of the USD, or is it also necessary for Hydra to be fully functional?
do you want to take that one, Aura? Like which plugins are necessary to run?
Yes, sure. So Hydra is completely decoupled of a USD file. It is not bound to that. You just have to implement a sim delegate and a render delegate. It just happens that they live under the same repository because I guess Pixar uses everything together and it's there, but they are independent kind of libraries. So, and for the plugin system, yeah, sure. Go ahead.
Yeah, so what would the size be if I don't want to have a USD imaging kind of, if I just want to have Hydra and then just provide my own delegates? Did it have an effect on the size?
Yeah, the 1 point something, that's the 1 point something.
So
Okay,
all the
cool.
plugins are that we load right now. This is a question for you, Aura. All the plugins that we're loading now are to load USD files. It is not necessarily to make Storm fully functional. Or are some of the plugins on the Storm side?
Some, but not all. There's like
Okay.
the USD shaders and but that's what I'm saying. It would be interesting to have it like separate thing. It was more like a POC where we just have a main library that build one monolithic thing. But ideally, if we want to make it to production, I think we should have the concept of these different modules separated. And again, then there could be cache, or you could treat it differently as you would do on the web context.
Would that require like dynamic library loading in WASM?
Yes, Mscripton introduced one, and one they have like 2 ways of implementing, but yes, and I have seen other libraries that use it. So, for example, there's this Python on the web called Pyodide, and basically, if you go there, I mean, it's interesting. They have like a console, and then you can do something like, I don't know, import NumPy, and then you can see that they do an HTTP request, or they do a DL open, or I don't know if they use the other path for dynamic libraries for Mscripton, but it's support. It's just some work to do.
Mm-hmm. Were you able to get like asset loading, like images and others with the plugins that you statically linked?
Not sure I get the question. Do you?
In your examples, I noticed that the assets, the models didn't have textures, or maybe I didn't notice the textures. Were you able to get, if a USD references PNG files or other texture assets, did you implement sort of the asset resolution or asset loading?
That comes with the USD. So that's one of the things that comes, that there's like one piece of just the whole library that it's called asset resolution.
Yeah.
And we do have a texture in one of the models, the gearbox. has like a bomb mapping kind of texture.
Okay, thank you.
And there's a few hands up. Cheryl, did you want to go first?
Yeah, thanks. Are you now supporting some kind of fancy plugins like the USD skeleton, both on the USD and the imaging side?
So they built. I haven't tested all of the USD capabilities. We focus on what we wanted to achieve first, but possibly. I mean,
Yeah, okay.
it's built. We don't
With
put it. We
with
just
my
cherry
limited
pick.
Okay, with my limited experience with how the plugins load and run, apparently the Hydra system or USD is loading all possible plugins, and then you load the content. Would it be a way of basically, depending on the USD stage you are dealing with, you kind of detect that you are, for example, USD using a specific primitive like the USD skeleton, and then you download on demand the WASM part of it, just to
Yeah, that's what
minimize the initial. Yeah.
Yeah, that's what I think that we should do. I run into a couple of cases that I didn't load a model and it did the request and it couldn't find it because I didn't pre-bake it. and that's why I contributed to the site. I cherry picked like 10 plugins that maybe not all the models are using all of the plugins, but so that's what I say that there hasn't been much optimization going just to get it working. But that's exactly what I'm saying, that how it should look, that it should do depending on the stage, you get the particular plugin and then you can do requests.
Yeah, I mean, there's certainly a lot more work to be done here. We just wanted to get the code out there if other people are interested, and especially ahead of SIGGRAPH and with the other work that we released on the DX backend. There are some open questions. How do we streamline the management of shaders across all the different APIs and things like that? So it's a pretty early version, and we would love more people to contribute and solve some of these problems that remains. But we just wanted to share the work we've been doing so far with the rest of the community.
It's great work, by the way.
I have another question. Can you talk a bit more about the interface between WebAssembly and JavaScript? So for us, for example, the majority of the code is in JavaScript, and I just wonder how difficult it will be to basically use Hydra, which is WebAssembly. Do you see that like an application using Hydra is going to have to be mostly in WebAssembly, or is there going to be a good interface, and where does it sit in terms of data coming from JavaScript, like streaming, whatever, and then going into Hydra? Can you explain a bit how that may look like?
Yeah, I can start on that one. Feel free to add, Aura. But yeah, I think for this to be usable or attractive for web developers, it needs to be through JavaScript, obviously. So we haven't spent that much time yet on that side of things. So you have some bare bones bindings for some of the API, but that's definitely a future area. But I think you want to be able to connect your JavaScript application to this and write all the business logic in JavaScript, except for maybe like some performance critical things that you want to go through WebAssembly. But for the most part, the high level logic, I would expect people to want to write in JavaScript. That's our thoughts, at least. Aura, anything to add?
Yeah, nothing. So actually we did this 3JS render delegate and it bounced a little between the Hydra and 3JS app. I'm just trying to find the link so that you can see it. So this is how the render. And it comes together. Yeah. And it just comes together with another C++ class, but theoretically should be, easy to do.
Okay, thank you very much.
I'm loving all the discussion. Other questions or topics?
In thinking about how to sort of marry GLTF and all the USD stuff, I noticed in your chart, Heinrich, that Hydra was like, you would take image or scene graphs and push them into Hydra. Is there any work on trying to directly import like a GLTF scene into Hydra?
Absolutely, yeah, you could totally do that. So I think we have that in some of our, example viewers internally. So yeah, you can make a loader for any sort of format. So to deploy this in the web environment, yeah, GLTF would obviously make a lot of sense.
Cool.
I mean, first, look, huge thanks for open sourcing that. I mean, I think that sparks these kind of discussions, this kind of collaboration, and hopefully moving the world forward. Is Autodesk planning to do like continued full-time development on this, and is there any bit of a roadmap?
Yeah, I mean, we're still kind of in the research phase, I would say, and trying to figure out like what are the main remaining things to solve before we can look at productizing this, or using it in some of our products. But I mean, so far everything seems very promising, and obviously we can't really disclose any forward-looking roadmaps, but yeah, our intent is obviously to continue this work. Otherwise we wouldn't have started, but I think it's a benefit to the a lot of potential people outside of Autodesk, so that's why we open source it, and we're very interested in contributions to this work, obviously.
Cool. Other questions? Okay, so we're right on time, so why don't we wrap up the official part of